In this section, we will look at the calculation of rates in the work of public health. A rate is a ratio of a numerator over a denominator that includes a component of time, and that component of time is the same in both the numerator and the denominator. In public health, the unit of time most commonly used is 1 year, and many times we actually get sloppy in expressing rates and do not explicitly state per year. So for example, if there were 20 deaths in a population of 1,000 in 2018, the death rate is often expressed as 2%, but in actuality, it is 2% per year, or 2% in 2018. Let's look at Community X, but specifically for the year 2012. In 2012, there were 40,000 females aged 13 to 19 years, but in that year, it was 800 teens that got pregnant sometime between January and December of 2012. 39,200 teens did not get pregnant in that time period. So what was the rate of teen pregnancy in 2012? The calculation is shown as follows. It was 800 out of 40,000, or 0.02 in 2012. Now, for ease of comprehension and expression, we usually express rates as per a certain population size. For example, we might say percent, which is per 100 individuals, or we might say per 100,000 individuals. Using a standard population measure is easier to express and allows us to compare across populations. So in our example, the teen pregnancy rate in Community X in 2012 was 0.02 in 2012. This is a very awkward measure that does not mean a lot to most people. Applying that to a standard population of 100 allows us to say that 2% of teens became pregnant in 2012, or applying it to a standard population of 1,000 allows us to say the teen pregnancy rate was 20 per 1,000 population in 2012. Now, think about how you would express each of these rates in a phrase if you were talking to a non-public health expert. So we might say, for the first expression, that there were 0.02 pregnancies per teen female in 2012. When we apply that to a standard population of 100, we would say that 2% of teen females had a pregnancy in 2012. And per our standard population of 1,000, we can say that there were 20 pregnancies per 1,000 teen females in 2012. And thus, rates can allow standardization of a measure so that two population, two scenarios, or 2 points in time can be compared. So let's consider this question. In Community X, is teen pregnancy associated with a decreased chance or decreased rate of obtaining a high school diploma? To answer this, let's look at our group in 2012 and follow them forward through 2018 to see if they obtained their high school diploma. This is how we depict our population. We had 800 teen girls who became pregnant at some point in 2012. 400 of those graduated from high school, and 400 did not graduate from high school by 2018. Of the 39,200 females that did not get pregnant in 2012, as of 2018, 31,360 graduated from high school, and 7,840 did not graduate from high school. Using rates will allow us to better compare these two populations. As you can imagine, looking at the numerators as they are presented here is actually quite difficult to compare. Let's see what happens when we use rates. Our question of interest is teen pregnancy associated with a decreased chance of obtaining a high school diploma? To answer this question, take a moment to calculate the high school graduation rates among teens who got pregnant and among those who did not get pregnant in 2012. Remember to standardize your population. For this example, use a standardized population of 1,000 individuals. Let's look at our rate comparisons. The graduation rate in teens who got pregnant is 400 out of 800, or 500 per 1,000 teens by 2018. In contrast, the graduation rates in teens who did not get pregnant in 2012 is 31,360 over 39,200, or 800 per 1,000 by 2018. You can see in this direct comparison that you are able to see that a higher rate of individuals who did not get pregnant graduated from high school as compared with female teens who did get pregnant back in 2012. There you can see the power of using rates in epidemiology in order to form population comparisons. So far, we have discussed calculation of rates using number of people in a population as our denominator. This works well in the majority of applied public health work settings. However, as epidemiologists, we are frequently considering a study setting where you are actually following a specific group of individuals over time. In that situation, an alternative option is to calculate the amount of observation time in your group or cohort that was contributed to your study. Consider our example of observing teens from 2012 to 2018 to see if they obtained their high school diploma. Now, keep in mind, some of those teens who became pregnant at some point in 2012 might have left our community in the subsequent 6 years. Some of those teens might somehow have fallen off of our radar. They did not want to be contacted by us, so we don't actually know what happened to them. Calculating a denominator in this specific way can be expressed as the person time at risk of a particular event, and this event can be negative, such as a disease occurrence, but also can be positive, such as our example of high school graduation. But this method allows for inclusion of observation time of those who left your study or had an alternate outcome such as death, which would preclude their ability to graduate from high school or be observed through the year 2018 without obtaining their high school diploma. This results in an accurate calculation of the rate of an event in a particular population that is actually at risk for that event. The most common use of person time is the measure of person years, but you can also do person days, person months, or any other measure of your choosing. The person time denominator is essentially the amount of time that each person is observed during which they are able to achieve the outcome that you are interested in capturing. Let's look at this graphical depiction of our specific study of interest in a specific number of 5 individuals. Our observation period is 6 years, 2012 to 2018. Let's imagine person 1 was observed for 5 years, but then they were lost to follow-up. They were no longer interested in being contacted by us. Person 2 was observed from 2012 to 2017, or 5 years, and graduated. Person 3 was observed for 4 years and graduated. Person 4 was observed for the full 6 years and did not graduate. And person 5 was observed for the first 2 years of our study period, but then was lost to follow-up. Let's take a moment and in this example, calculate our actual person time. The first thing we remember is that 2 people had our event of interest, or graduated from high school. Now, what is the denominator in this question? Because the high school graduation rate we will calculate is the number of individuals who graduated divided by the total person time contributed by all individuals that we observed. The calculation of person time is as follows: 5 years for person 1, 5 years for person 2, 4 years for person 3, 6 years for person 4, and 2 years for person 5. That's a total of 22 person years. And you have to go back to remember that 2 people graduated. Given this information, let's take a moment to reconsider our graphical depiction to make sure that you understand where each of these numbers comes from. You can see in this both the amount of time that was contributed by each individual for the person time denominator, as well as the numerator events of graduation. So coming back to our example, we have 22 person years total contribution, and we have 2 people that graduated. So our high school graduation rate is 2 out of 22 person years, or 0.09 per person year, or 9 per 100 person years. Regardless of the denominator we choose, what can we do with rates? We can compare a rate that we measured today with a rate at another time or a rate in a different population. We can compare and combine findings with other studies, and we can observe trends over longer periods of time. Rates are an extremely powerful measure that are frequently used in epidemiology and therefore very important to understand. So in summary, numerators are counts of events or people. Denominators comprise the population from which numerator events are drawn. Ratios compare two or more numbers, while proportions relate a part to a whole. And finally, rates are ratios with time implicit in the denominator. Thank you for joining us in this course.